Nothing coming back.
So I would like to remind everyone about the evaluation form. So if you're a student, TA, or mentor, or presenter, so please make sure you fill the necessary forms. I think we are live now on YouTube. So Geraldo, maybe you can start anytime.
Thanks everyone for joining the seminar class. Today is my pleasure to introduce Onur. He's going to talk about the Good Neural Network paper that we published in PACT 2021. So Onur is an electrical engineer and undergraduate exchange student from Australia, and he's interested in power systems and machine learning, and he has prepared his presentation with some special points for us today. So enjoy.
Thanks, Geraldo. So today I'll be presenting the paper on Google Neural Network models for edge devices, analyzing and mitigating machine learning inference bottlenecks. It was presented at the PACT 2021 conference with the following researchers. So first I'll provide a brief executive summary of the research. So the problem that is addressed in the paper is that Google Edge TPUs suffer from three major shortcomings, and that's low throughput, computational throughput, low energy efficiency, memory access, utilization bottleneck, and this leads to an area for improvements. The motivation and goal for the research is that the monolithic design of the Google Edge TPU is only suitable for a specific type of a neural network model. So the Edge TPU does not cater for heterogeneity across different neural networks, models, and layers. The key approach used by the authors is to propose a new acceleration framework called Mensa, and it incorporates several edge machine learning accelerators, and each of which caters to different models and layers. The key results proposed by the paper is that Mensa improves the energy efficiency and throughput by 3 times and 3.1 times over the default Edge TPU, and by 2.4 and 4.3 times over Iris v2, where Iris v2 is a comparable state-of-the-art accelerator. So a brief outline for today's presentation is that I'll be talking about the background, the TPU and model characterization, the Mensa framework, an application on Google Edge neural network models. Then I'll provide an evaluation of the accelerators, some strengths and weaknesses, key takeaways, and discussion. So first I'll talk about the Google Edge TPU. So the Google Edge TPU, Tensor Processing Unit, what is it? It's a purpose-built ASIC, which is an application-specific integrated circuit, and it's designed for a specific task. In this case, it's designed to run machine learning inference at the edge. What is the edge? The edge is the opposite to the cloud, where instead you run the code on-premise. So you can physically buy the chip and then, or the device, and then run your machine learning algorithms. Some advantages are that because you have the chip locally, there is less network latency. You don't have to communicate with the cloud, so there's more bandwidth as well. It's great for Internet of Things devices because they usually generate frequent data, and it reduces power consumption because of its small form factor. It's also low cost, so it's entry level, and it can be integrated easily with Raspberry Pi and such devices. So there it is, Coral GPU made by Google, and it's pretty small. It's like the size of like a paperclip. The challenge is that the Edge ML accelerator, it has to execute inference across a wide variety of neural network models. In this specific study, we look at 24 neural network models. So the first 6 are RNNs, which are recurrent neural networks, transducers, and they're specifically used for speech recognition. Then there are LSTMs, which are long short-term memory models, and they're used for language translation. And we have RCNNs, which are recurrent convolutional neural networks for image captioning, and then CNNs, which are convolutional neural networks, face detection. And as you can imagine, if we try to use all of these different models on a specific device, it may not work so well for each type of model. So now I'll talk about the TPU and model characterization. So I'll provide analysis and then some shortcomings and some causes for these limitations. So the analysis was conducted on 24 Google neural network models. These are edge Google neural network models, so they're not publicly available. And the researchers measured the throughput, the energy efficiency, and memory utilization. For the throughput analysis, we have this following graph, which has the vertical axis measured in teraflops per second, and then the horizontal axis in flops per byte, where a flop is a floating point operation. The dotted line is called the roof line, and that is the sort of theoretical peak energy efficiency. And then each data point is a model in the neural network, is a neural network model tested. And something that we can see already off the bat is that CNNs and RCNNs only operate around 52% of the peak throughput. But what's more concerning is that LSTMs and transducers operate at less than 1% of the peak throughput. So not great. The key takeaway from this graph is that the accelerator operates significantly below peak throughput across all models. Now for energy efficiency analysis, we have a similar graph, but this time it's in teraflops per joule. So it's measuring the energy efficiency. And we have, again, a roof line where the ideal energy peak efficiency would lie. Again, we see the best CNN model is only operating around 50% of peak energy efficiency. And again, LSTMs and transducers operate at 33% of peak energy. The takeaway here is that the accelerator operates below the upper bound energy efficiency across all models. For memory access, it's a similar story again. And for this graph, we can see normalized energy against the various neural network models. And we can see that most of the energy goes towards off-chip parameter traffic and distributing parameters across the processing element array, where the processing element array is in blue, and then off-chip interconnect in gray. We can see the energy distribution for that. So now, to summarize the major energy, so the major edge TPU shortcomings are first that it operates below the peak computational throughput, below the energy efficiency, and the memory access system is bottleneck. So what are some causes for this performance bottlenecks? Well, we can look in this graph here, which shows the various layers inside the neural network models. So the vertical axis is flop per byte and horizontal is parameter footprint. And as we can see, they're quite spread out across the different layers. And we can see as well that the CNNs and RCNNs group into some sort of group. And then the layers from the LSTMs, transducers group into a different group. So the takeaway here is that there is variation across the layer characteristics in the models. And by the way, when I mean layer, I mean in each neural network model, there are sometimes multiple layers. In a similar case, we can see that match operations, which are multiply accumulate operations, and flop per byte varies across the layers significantly. So we can see that there's 200 times variation in MAC intensity, 244 times variation in flops per byte. So there's variation in terms of layer characteristics. All of the don't help the edge TPU. So the main takeaway is that the Google Edge Tensor Processing Unit does not cater layer heterogeneity. And this is because of the design architecture of the edge TPU, where Google has taken a monolithic approach to designing it, where they've got fixed devices in the chip, which do not cater well to various neural network models. Cool. So now I'll talk about the Mensa framework, which is the proposed solution to this problem and how we can mitigate these issues. So the goal of Mensa, the goal in general, is to design an edge accelerator that can efficiently run inference across the different models and layers. Currently, on the left, we have the edge TPU. You can feed it all the models you want, and it will go straight into the monolithic design. And Mensa proposes this sort of design here, where instead you feed it the models, and then it goes through the runtime scheduler. The runtime scheduler will take the layers from each model and then class them into families. And then those families cater to specific accelerators. So instead of having a single accelerator, there are now multiple accelerators, and they cater to specific families of layers. The runtime scheduler, its purpose is to identify which accelerator each layer in the model should run on. And each accelerator caters to specific layers. Something interesting that the paper finds is that the layers tend to group into families. The heuristic checks the following. So the runtime scheduler utilizes a heuristic, and it checks whether an accelerator is best suited for a specific layer, and also which layers have a high interlayer communication, because it's not exactly worth to put two layers that have high communication in the separate accelerators, because then they'll need to talk to each other, and that's not very efficient. So it would be best to put it in the same accelerator. So the scheduler works as follows. You feed the neural network model into it and some characteristics of the accelerators that are pre-designed. You also have to provide layer characteristics of your neural network model. This is all manual. And then the scheduler will provide you layer mapping, which layer goes to which accelerator. So now I'll talk about an application on the Google Edge models, which is Mensa G for Mensa Google. And I'll talk about classifying layer families and the different types of accelerators. So in these graphs, we can see the flop per byte against parameter footprint and macro operations. And what was found is that we can group these specific layers into families. So these are the compute-centric layers because they have low parameter footprint, high data reuse, and Mac intensity. So those would be like families 1 and 2. And then we have data-centric layers, which have high parameter footprint, low data reuse, and Mac intensity. So that would be families 3, 4, and 5. Now, already you can notice that there's a red point there. It's not within one of those circles. And that's already one of the weaknesses, is that these families are all manually selected. They're all manually designed. And so how do we deal with outliers? I'll talk about this later. Before introducing the accelerators, I think it's important to talk about the accelerator data flows because they vary. The point of the data flow is to determine how data moves between the components inside the accelerator, and each accelerator is designed alongside a specific data flow. This will optimize the reuse of across the layers. For example, if you consider the weights in machine learning, they can vary. So some have weight, others will have less weight. Have less weight, you can store them in parameter buffer. If you have a lot of weights, you should store them in DRAM instead. For the first accelerator, it's called Pascal, and it looks like this. It caters to families 1 and 2, which are compute-centric layers, and therefore it's an on-chip accelerator, so it resides on the TPU. It has 2 teraflops per second, and it has an 8 times reduction in the activation buffer compared to the baseline, the default Edge TPU, and it also has 32 times reduction in the parameter buffer. The next accelerator is the Pavlov accelerator. Looks like this, and it is catered towards family 3 layers, which are LSTM data-centric layers. And so this is a near data accelerator, so it utilizes processing near memory. It has 128 gigaflops per second. It's got a 16 times reduction in the activation buffer, and this one doesn't have a parameter buffer. So it will stream the weights and parameters using the inference directly from DRAM. The last accelerator is called Jakar, and looks like this. It caters to families 4 and 5, which are the non-LSTM data-centric layers. And this is also a near data accelerator, and it has similar parameters. However, this one does have a parameter buffer. Cool. So now I'll talk about the evaluation of accelerators. So the evaluation methodology employed by the researchers, the throughput study, an energy efficiency study, and then the conclusion on results. So the evaluation was done in simulation to compare Mensa against the baselines. So there are 2 baselines that you'll see. The first one is the default edge TPU baseline, which is just an unmodified TPU. And the next one is the edge TPU with high bandwidth memory, more specifically 256 gigabytes per second. The first study is the throughput study. So we have normalized throughput against the different neural network models, and at the end, the average. We can see that the Mensa G improves throughput by 3.1 times on average compared to the baseline. But actually, you can also see that the baseline plus high bandwidth is not doing too bad either. For the energy efficiency study, we have again graphic normalized energy against the neural network models, and we can see that Mensa G improves the energy efficiency by 3 times compared to the baseline. For latency, we have again normalized latency against models, and we can see that Mensa is able to reduce the latency of the baseline and the baseline high bandwidth memory on average by 1 and 1.17 times. For the processing element utilization, we have this graph, and we can see again that able to improve all the models on average, the utilization by 2.5, 2 times, 2.6 times over the respective baselines. And the last one is the comparable state-of-the-art accelerator, which is ISCA. In conclusion, the problem that is addressed by the paper is that Google Edge TPUs suffer from 3 major shortcomings, which is low throughput, low energy efficiency, and poor memory access utilization. The motivation of the research is that currently there's only one design, and it can cater to only a specific type of model. So the Edge TPU does not account for differences across layers and models. The key approach employed by the authors is to propose a new framework, and it incorporates several machine learning accelerators, each of which caters to different models and layers. And the results are that the energy efficiency and throughput is improved by 3 times, 3.1 times over the Edge TPU, 2.4 and 4.3 times over the state-of-the-art accelerator, RSP2. Cool. So now I'll talk about some strengths and weaknesses paper. The paper reveals a novel observation, and that is that the layers from several neural network models, they group clusters, and this could inform future research in neural network acceleration. The authors conducted the first comprehensive workload bottleneck analysis with Google Edge TPU on the Google Edge network model specifically, and they found that heterogeneity exists in and across neural network models. It advocates for more frameworks like Mensa to provide heterogeneous acceleration for both existing and yet to be developed models. There was a rigorous evaluation for the performance and energy benefits of Mensa and on the design for Google Edge neural network models, and the paper used appropriate language except there were a few typos. Some weaknesses of the paper is that it's not discussed the limitations of the proposed framework, like the scalability or the complexity of implementation, and if that is compatible with other hardware and software. Further research is needed to evaluate the limitations and scalability and compare it with more accelerator frameworks. The author mentions that Mensa typically needs to employ a small number of accelerators, but it is unclear how this translates into actual performance gains. So there were 3 accelerators used in this study, but it's unclear if using 2 or 5 would actually benefit. The runtime scheduler is a heuristic, and so it is suboptimal. The paper uses an ad hoc methodology to identify layer families. As I said before, it's done manually. And clustering of layer families, some layers are not clearly classified into families. For example, I gave you the example of the one layer that was not classified properly. It's limited to analyzing the Google Edge TPU and Edge neural network models, which may not generalize to other hardware models. Again, the Google Edge neural network models are not available to the general public. And so if we were to use it with our own models, it might not work the same. For example, if we were to use large language models, such as this guy, it might not work the same. The paper could briefly explore the impact of Mensa on the accuracy of the neural network models. I discussed this with my mentors. We don't think there would be any impact on the accuracy itself, more so the throughput and the energy efficiency. However, when you're trying to get consumers to adopt your product or your acceleration framework, it's always better to know that it doesn't actually affect the accuracy, but this was not explored. So key takeaways from the research paper are the novel contribution that it was the first work to examine the bottlenecks of the Google Edge TPU when executing on models. It quantified the interlayer variation that exists within and across the models. And it identified that layers can be clustered together based on several shared characteristics. It proposes a new framework for ML inference acceleration. It's called Mensa, with both on-chip and near-data accelerators. And it evaluates the performance and energy benefits of using such an acceleration framework on the Google network, on the Google neural network models. However, further research is needed to evaluate the limitations and scalability of Mensa and to compare it with more frameworks, acceleration frameworks. Do you guys have any questions? Cool. Let's move on to the discussion. How could we optimize the runtime scheduler to better classify layers? So to refresh your memory, the runtime scheduler uses this sort of approach where we feed it the neural network model into a scheduler, and then we also have to give it the accelerator characteristics and the layer characteristics, and then it outputs the layers. But the part on the left is done manually, so we have to give that information. Is there any ideas on how we could optimize the runtime scheduler? Then I'll continue. The runtime scheduler only continues the next layer in the model, which is one of the limitations. You could improve it by taking into account a global view of layers instead, inside and across the models. So for example, you could use a meta heuristic for global search instead of using like local search, and then you could find the maxima, global maxima instead of the local maxima, and this would better classify layers. And this would be more applicable to consumers because, like I said before, we may not use the same models. We might use different models that haven't been tested specifically in this case. Some related research for this particular discussion point is a paper that was presented at ICLR in 2017, the conference in 2017, yeah. And it's called Designing Neural Network Architectures Using Reinforcement Learning. Paper shows that they can automatically generate high-performing CNN architectures for a given learning task. And it explores a large space of architectures, iteratively discovers designs with improved performance on the learning task. So ideally, we could use this research to create a model that could automatically create the layer characteristics and CNN architectures, not only for CNNs, but also for the other models. For this paper here, neural architectures search with reinforcement learning, also from the same conference. It uses a recurrent neural network to generate model characteristics of the neural networks. And if we have a way of generating the characteristics automatically, then we can feed these straight into scheduler, runtime scheduler. All right, another discussion point is why are 3 accelerators used in Mensa G and not like 2 or 4, 5?
Before that, there's actually one question.
Can you read the question?
So the question is in one of the diagrams you mentioned the performance of baseline plus HP. If we again say what HP is and for and why it shows similar performance compared to Mensa and context. Because there are 3 layers, 3 different clusters.
Yeah, so we have a normal default baseline, which is the default HTPU, it's unmodified. And then the second one is the baseline with high bandwidth memory. So that's baseline plus HB. And it utilizes 256 gigabytes per second. So hopefully that clears that up. Why do we see a comparable sort of performance between between Mensa and the baseline plus HB? Personally, I believe that it's because the high bandwidth memory is such that it allows the TPU to utilize more data in the data flows, as I previously showed. And so if there is high bandwidth, then it can perform similarly based off the different accelerators that we used before, even though there's only a single accelerator, because it's still a baseline. So hopefully that clears that. Okay, back to here. So why do we use 3 accelerators in Mensa G? Well, the accelerators were manually designed. So it's not like they were automatically designed. In this case, we found that, or researchers found that 3 accelerators would work well. However, some layers were not classified into the proper families, i.e. like this one here, because it was manually designed. And so you deal with some outlier layers, and potentially it's a problem because you can't classify those easily into the separate families. So then maybe an approach to fixing this could be to train a machine learning model to dynamically design the accelerators. But how many accelerators would be required? Still not clear. Perhaps it's a hyperparameter that you can use cross-validation to test and to test different amount of accelerators and find which one's ideal. And how do we deal with the outliers? Still unclear. But as such, a framework could look like this, where instead of having 3 accelerators, there's just n accelerators, and they could be dynamically designed by a machine learning model. Some related research in this field is towards automatic and agile AI/ML accelerated designs with end-to-end synthesis, which was presented at IEEE ASAP in 2021. The framework targets AI/ML ASICs accelerators, which in this case is directly applicable to the edge GPU. And it performs optimizations that combines specialized architectures and templates and to synthesize accelerators automatically. So you could run this particular model to synthesize your accelerators, and then you would be able to dynamically create them instead of manually. Next discussion point is processing memory advantageous for machine learning accelerators? Any thoughts? Well, we can already place some of the computation logic inside the logic layer of DRAM. For example, Pavlov and Jacquard already do that. But 3D stack memory is costly and it's low capacity. So instead, we could use different memory devices like UpMem or Samsung's high bandwidth memory and processing in memory device, or GDDR6, where UpMem looks like that, and then Samsung's device looks like that. In fact, you could probably even integrate UpMem straight onto the edge GPU. For example, if users require more performance, they could purchase these modules and then integrate them. However, I believe the UpMem modules are actually larger than the TPUs themselves. You could probably scale them down. Something else to consider is that the granularity of computation, where you break down large computationally intense tasks into smaller subtasks, and this would allow you to integrate back operations inside these various devices. So the UpMem or Samsung's device. However, some devices don't have floating point units, but they also might have great capacity. So it's always a trade-off to consider. And some related research comes from the Safari group, which is accelerating the neural network inference with processing in memory from the edge to the cloud, which was presented at IEEE Micro 2022. And this successfully implemented UpMem architecture for neural network inference, which is exactly the problem that we're dealing with here. The benefit of using UpMem is that it's programmable and scalable. It advocates for 3D-based processing in memory, and this is also employed by Mensa. So this is very applicable to this specific research. All right, for the next point, are the limitations of edge devices comparable to those of the cloud, or specifically the Google Cloud? Yep.
I think there are just two completely different problems.
In what way?
Edge devices they don't have the same power capabilities. And they have, but there's no latency to communication. So
yeah. So if we talk about this, edge devices, they have limited machine learning models, at least compared to the Google Cloud, which has multiple compatible machine learning models. In the cloud, the potential for heterogeneity is higher. Google offers a service called service computing, which is just larger scale than edge computing. So you often get large gains as well. And the cloud, however, still needs to address the problem of classification and scheduling, which needs to be dynamic, which is a similar problem that is dealt with in the edge GPU case. So some related research in this is the paper from ISCA 2017, which is in data center performance analysis of a tensor processing unit. This is actually the first performance analysis of the cloud TPU, and it was found that there are similar limitations compared to the edge GPU, where the scheduling of the layers and classification has to be done dynamically. And yeah, any questions? All right. If no more questions, then I'd like to thank my mentors, Geraldo and Rahul, for the past 2 to 3 weeks, and for being very supportive and answering many questions. It was a very interesting research paper, so thank you.
Geraldo, I think you may want to provide comments or feedback.
The talk was really good talk. Maybe I can give some perspective on paper, since I'm part of one of the authors. So this paper was done when the first author and Raleigh was at the internship at Google, 2019, and I was there at the same time. I worked on another project, and we worked together this particular paper. And I remember in the beginning, basically, the Google, the STQ team gave Mariah STQ version 2 and a bunch of workloads, and he started doing those plots and collecting the data and doing the profiling. And then he saw that there was like a massive amount of underutilization of this hardware that the people in Google themselves designed for those models. Why? There's no reason for, like, you are designing your own hardware for your own application, so why you are provisioning so much? And then this was the main idea that led to Mensa, the framework itself to get into different types of neural network models. If you look, actually, it's a bit funny because if you look at the next generations of if you look at the next generations of the CPU itself, instead of the 8th version, the large versions. Actually, what the Google has been doing until generation 3, I guess, was over provisioning even more and more, especially in terms of array size. And then if you look at the CPU version 4, if I'm not mistaken, there is a drop, there is a reduction in some of their hardware resources from the previous generation. And then you can see that this is understanding that, like, over provisioning in those accelerators, even the one for the cloud, is not so attractive because, again, it's virtualization. So heterogeneity is always good. It brings a lot of cost of scheduling and how much heterogeneity support and all of those things that was mentioned at the top. But it's a good way of thinking about this type of problems. So I guess this is basically that. Thanks, Mohammed.
Thanks a lot, Geraldo.
Just give me a few minutes and upload these slides. How have we doing it? Joel, would you be introducing the next presenter?
Yes, can you hear me?
Yes, we can hear you.
All right, okay. So are you ready in the room?
Yes.
Okay, very good, thanks. All right, so our next presenter is Sven Fischner. He's a computer science student in his last bachelor semester, and he's planning to continue his studies with a master's and focus on machine learning and visual computing. So he's greatly interested from that perspective in software and hardware aspects of machine learning and data science. And he'll present another accelerator paper, perhaps from a bit different perspective than the previous one, an entirely new accelerator architecture. So I'm very excited about this, and please, Sven, take it away.
Thank you. So welcome to my presentation and discussion about the research paper Think Fast, a tensor streaming processor for accelerating deep learning workloads, as presented by Grok Inc. at the ISCA conference 2020. So let's start with a quick summary. First of all, the paper observes that machine learning workloads exhibit abundant data parallelism. And this can be readily mapped into tensors in hardware. And a simple processor would produce a consumer pattern stream programming model, can enable precise reasoning and control of hardware components, which then means that we can achieve good performance and power efficiency. The key ideas here are to use tensor streaming and to use this to design a specialized hardware architecture that achieve significant speed up for various deep learning computations. The implementation, this is implemented via a new deep learning processor architecture that features a dedicated tensor streaming unit and carefully optimized memory hierarchy. The result that the paper gives us is a novel hardware software approach to achieve fast performance on machine learning workloads. And they claim to have a significant improvement for resonant 50 classification. Now let's jump into a more thorough discussion where I would first like to give you a quick background on deep learning and tensor computations and what it requires from the hardware. Then we will take a look at the proposed architecture from the paper and how this is implemented and the results this gives us. And in the end, we will look at the takeaway and conclusion. Okay, so let's start with the background. First of all, what is deep learning and what are its hardware requirements? Deep learning basically is the training and deployment of neural networks like image recognition or natural language processing. And as such, it involves large amounts of data. We need to process a large amount of data. Traditional GPUs and CPUs are not necessarily always that efficient for such large amounts of data. We will see why in a minute. Development of specialized hardware is thus really interesting. And this is generally done by using ASICs or FPGAs. One thing that all these solutions have in common is that the hardware must be optimized for parallel processing and memory bandwidth because we have that much data to deal with. So the CPU, why can the CPU not be used in an efficient way for this? Because it's not designed for massive parallel processing. Of course, CPU can do parallel processing, but not to the extent that we need for such large amounts of data. We have a few cores or even threads, but not as many as we need. And also a CPU must compute many other things. It must keep track of various other tasks or even the operating system. So it's not fully free for the machine learning task. And it is limited in the handling of large amounts of data in a timely manner. We only have a low on-chip memory. We maybe have some cache, but it's very limited in size, and the most of the data must come from the storage. The GPU, on the other hand, is actually designed for parallelism, and thus it's also widely used for machine learning. Here, the thing is that it's not made for such large-scale operations. We have really large tensors that we need to work with in machine learning for convolutions or matrix multiplications. And the GPU can have problems with this because it has a limited compute throughput. And this leads to batching of data where we need to take the data and batch it into smaller batches, then process on them, which is not as desirable as having a batch size of 1, so it's processing each data on its own. Also, the memory bandwidth for GPU is also a bottleneck, because here again, we need to get all the data from storage. Another thing that these general processing units have in common is that they're not fully deterministic, because they do a lot of optimization and reordering in hardware. One important example for this is instruction reordering. And just because this is so important, let me give you a short example to remember you what this actually is about. So assume you are a programmer and want these 5 instructions to be executed. Then the system might take a look at them and see that instruction number 2 actually is dependent on instruction number 1, because we need to read a registry that number 1 writes to. Similarly, 3 and 4 might be dependent on 2, but 5 is not dependent on any of the previous instructions. So if it is in some way beneficial for the pipeline or efficiency, the system might decide to reorder these instructions, which does not change the outcome in the end, but it actually changes the sequence of instructions. So it's not deterministic because it's not exactly what the programmer told it to do. And this is important, and we will see later on why. Another thing is tensor computations. What are tensors? We have essentially tensors are multidimensional arrays. And we can see that here. A rank 0 tensor is just a scalar, rank 1 is a vector, rank 2 is a matrix, and it goes on like that. Convolutions, for example, are important for machine learning if they're just operations on tensors. But why are tensors so difficult to work with? First of all, they can be big data objects and require many memory accesses. Also, tensor operations might involve strided access patterns. An example for this is if you have a matrix that is stored in row major and you want to perform operations on it in a column major way. This means that the data you need to access is not sequential in the memory. So if you use caches and the caches load blocks of memory into the processing unit, the next data that you need might not be in the cache, and this leads to a lot of cache misses, which is not good for performance. Okay. So now let's take a look at the proposed architecture and how it actually solves these problems that I've mentioned. The paper introduces Think Fast. This is an architecture that uses the streaming model. This means that data is processed as it streams through the processor. It also has multiple processing elements that can perform tensor computations in parallel. And whereas performance optimizations like scratch-pad memory or low latency interconnect, we will also see them in a minute. The takeaway here is that Think Fast aims for high performance and energy efficient acceleration for deep learning workloads by addressing all these problems that I've mentioned in the background. How does it do this? So it uses functional slicing, and for that, consider this conventional chip multiprocessor that contains independent cores that are interconnected with a network for data exchange. And each of these cores has does instruction execution over several stages. You can see these here, just canonical exchange pipeline that you probably know: instruction fetch, instruction decode, execution on the ALU's memory access, and write back. The Think Fast uses functional slicing, which is taking this and reorganizing these homogeneous two-dimensional meshes of cores into a functionally sliced microarchitecture. So we essentially are disaggregating the basic elements of the core or the respective function. You can see these different slices with the different functions here color-coded, these vertical parts of the chip. So in the end, we have a slice that is responsible for the instruction control and dispatch, it's blue down there. Then we have memory. We have vector matrix multiplication, matrix multiplication, data exchange interfaces. Here, the important thing is that the tiles of the slice execute the same instruction stream. So we have single instruction, multiple data. This is why it's important that we have an architecture that is deterministic, because we have these single instructions that operate on a variety of data. Okay, but how actually do these instructions and data move on the chip? the instructions flow northward from the ICUs. You can see that here, they go up there. And the data flows east and west between functional slices. Interlane movement is also possible. What I mean by this is, if you take a look at the horizontal lines here, you can switch a line by these SXM units. They just do a permutation of the line the data is stored on. Okay, this is quite theoretical, so let me give you an example with a simple element-wise multiplication of two vectors. So let's say we want to multiply these two vectors here. And obviously we could do it sequentially, just 1 times 6, 2 times 7, and so on. But we can also do it in parallel because these different computations do not depend on each other. And this is exactly what the TSP does. We can once again see it here. We have the ICU down here. We have these slices, we have the memory slices, a vector times matrix slice, and a memory slice. And just 4 instructions. So we just have read element 1, read element 2, multiply these elements and store them back. So what is happening is the first instruction is propagated up these layers, and a single instruction operates on these 3 different data. Then the second instruction is propagated up, and in parallel, these flow to the right. This is what's called a flow model, multiplied here, and then it flows back out. And we have our vector, which is computed in parallel. We can also see the comparison here. Left, we have vector addition this time on a regular RISC, and right is a TSP stream. So here it's sequential, and here the data flows from left to right, and one stream loads the first element, the second stream loads the second one, then they stream into the addition and stream into the next memory. Another thing of the TSP is the role of the compiler. The compiler is scheduling everything. So scheduling is entirely left to the compiler. Not only has this the nice additional effect that the ICU can be much smaller because it has no scheduling role. And the paper actually claims that their ICUs take only about 3% of total space. But the important thing here is, as the scheduling is entirely left to the compiler, the optimization is also left to the compiler, and everything is controlled by the programmer in the end. So this is highly deterministic. It does exactly what we want it to do. Okay, now let's see how the chip itself looks. We have these different super lanes. We have 20 of them, and each of these super lanes contains 16 lines. And these lines are always connected to the same instruction. So on these 16 lines, it's always single instruction, multiple data. That's the minimum vector length that we can operate on is actually 16. But as we have these 20 super lines, we can operate on a maximum of 20 at the same time, obviously, which gives us a maximum vector length of 320. We have 144 independent ICUs down there that can give out instructions, and we have 64 logical streams per lane. So we have 32 that go to the east and 32 that go westward. Then we have a VXM module, which stands for vector times matrix. This consists of a mesh of ALUs, and each can do pointwise arithmetic in these different lanes. We also have matrix times matrix units. These consist of independent 2D arrays, and they can do matrix operations on int8 or floating point 16. Then we have the ICUs down here. They do what you would expect them to do. They give you some interesting possibilities like instruction fetching, inter-slice synchronization, which just synchronizes the data stream between the slices. It uses sync and notify for this, and it also offers inter-instruction delay by a no operation. Good. Then we have 2 SXMs units. As said before, these are just to permutate the data between the different horizontal layers of the chip. And 2 memory units. These are essentially the scratchpad memory that I mentioned earlier. They have 30 bits of addressing per slice, 16 byte words with 1 per lane. This yields a total of 220 megabytes on chip SRAM. And the C2C. This is providing send and receive in case you want to use multiple chips, or if the chip needs to output something, you can exchange 320 byte vectors with this one. Okay, so let's see what results the paper mentions for this new architecture. First of all, they tried to map the ResNet 50 v2 image classification models to the TSP, and they gave an inference query that was performed in roughly 40 nanoseconds, which equals above 20,000 images per second. And the important thing here is on a batch size of 1. This is 2.5 times as fast as the Google TPU v3 with a larger batch size. They also report fast matrix operations, where memory slices can read over 400,000 weights from memory and then install them into these matrix times matrix arrays less than 40 cycles. So they're quite fast. They are to be used in computations. They also claim to have good value per transistor. They say that their design has 30,000 deep learning operations per second per transistor, and they compared it to Water 100, which they say has only 6,000 operations per second per transistor. So each transistor is utilized quite efficiently. This here gives you memory bandwidth bound. You can see that we have saturation point here between operations per byte and the throughput at a roofline peak. So this actually means, in short, that the chip is arithmetically limited, and the on-chip storage, the on-chip SRAM, actually is fast enough to provide all the computational units with data they can work on. So they're fully utilized. And second thing here are the red and blue dots. The red dots mean our compiler-generated code that is placed in tensors, that places tensors closer to the matrix times matrix multiplication units. And the blue ones are code that is hand-generated purposely such that it is further away. So they could compare how efficient, first of all, the compiler places these tensors and how the difference is if it's further away from the actual units. And you can see that it does not make that much of a difference down the road. Okay, another interesting thing is this is power utilization. And you can see that it uses a lot of power where all of the units are used in these conventional 2D layers for the ResNet 50. But in between these peaks, there is not that much of power utilization. This is because they claim that the chip can deactivate superlanes that it does not use at the moment. So if you only have short vectors, so low amounts of data, like you only need one of these 20 superlanes, it can actually deactivate the other 19 superlanes in the meantime. And so it should be really scalable and power efficient. Okay, so now let's take a look at the takeaways. First of all, deep learning workloads tend to be highly tensor oriented, and tensor operations have limited performance in CPU and GPU. So special hardware is really interesting. Data streaming provides a good alternative to the common architecture. The paper proves this by giving us concrete implementation that leverages SM, single instruction multiple data, and also has a large on-chip memory that limits slow access to off-chip memory. In short, data streaming has the potential to outperform other state-of-the-art architectures and can also be energy efficient, as they claim with their own design. So are there any questions so far? Okay. So then let me quickly give you my subjective opinion on the paper. First of all, what I really liked about it is that it's really innovative. The paper shows a new take on deep learning hardware and introduces a novel architecture by this data streaming model. I do not know if this has been used before, but I could not find anything meaningful. It gives effort in power efficiency, which is always important because not only does it reduce cost, but nowadays where machine learning gets more important every day, it's nice to also limit the environmental impact of the whole thing, especially now that power is not as easily available as it has been before. It is scalable. It has scalability in mind via these C2C units. So it can be extended to warehouse scale computers where multiple of these chips work together. It was not thoroughly discussed in this paper how, and we will take a look at that closer in the discussion later. Okay. Also, programming was introduced. So programming interfaces were given that are really developer friendly and still offer fine-grained parallelism and fine-grained control over the whole chip because it's that deterministic. And they added a nice interface to the paper. Okay, some weaknesses. First of all, the paper claims that this new architecture is like a holy grail that fixes all machine learning problems. But in my opinion, it's not that broad because it mostly focuses on deep learning. So it has dense matrices in mind. It does not really discuss computation on sparse matrices. And there is an extensive discussion and focus on linear operations, but not. It is not clear how well this might perform on models that require nonlinear operations like classification trees or k-nearest neighbors. Also, some claims are not fully explained. Like somewhere they claim that there are 4 times improvement compared to other GPUs, but they never really say which GPUs. You have to. They give you a source and you have to go there, and there is a website that has thousands of benchmarks and you have to dig through it. It would have been nice to get a concrete example here. Also, some diagrams in the paper are fairly complicated and low quality. It would have been nice if they were a bit more involved and accessible. And the testing was limited. So this is not the case anymore, but it was the case when the paper was released. At that time, the design was not field tested, only in their lab, and focused solely on ResNet 50 for benchmarks. I know that ResNet 50 is a good approximation for the overall performance, but it's not perfect, and it would have been nice to see a few additional tests. But this was actually the case because they received the silicon really close to the ISCA conference deadline, so they could not really add more tests, but still would have been nice and would have made the paper better. Good. So then let's move over to the discussion. I have prepared a few interesting questions here. Of course, if you have something else you would like to talk about, feel free, but I think these will guide us through a few interesting conversation points. So first of all, how could the architecture be extended to improve sparse matrix performance? I've mentioned earlier that this was not really discussed and is not really a part of the architecture, but how could we extend it such that it does well in sparse matrices? Yeah.
Compression to hidden and decompression at the end.
Yeah.
So you have to keep the compression.
That's a good idea, and that's also what I found. So one possible solution is to do something similar as QSparse, which is NVIDIA's solution. Their idea is to represent sparse matrices as dense internally by compressing the sparse matrices to a dense matrix, and then you can essentially just use the normal dense matrix operations on there. And you have some log indices that are multiplied to the matrix just to keep track of where each element is in the original matrix, and they compute that way. So they just use normal dense operations and beforehand compress the matrix. If you're interested in more of this, you can take a look at this paper, Design Principles for Sparse Matrix Multiplication of the GPU, published by University of California. It's explained in detail how this essentially works. Okay. Another idea would be to directly support compressed sparse rows in hardware. So consider the CSR format in memory, maybe even add specialized functional units like sparse matrix vector or sparse matrix matrix units. Just a reminder for those who are not sure, this is sparse matrix and this would be the compressed sparse row. So the matrix is essentially stored as 3 different arrays: a row pointer, column offset, and data. So you could directly look at the computations that way in the units and have specialized units for this. But the point here is that you need special units, which takes away a lot of transistors from other units. So you would really have to think about whether this is in any way beneficial or if it is too much of a specialization to consider these sparse matrices. I think it depends on the use case here. But I would also say that a solution like that from NVIDIA would probably be better because it gives you more flexibility. More research on this approach can be found on sparse core, stream ISA, and processor specialization for sparse computations at class 2022. Now, the next problem that I've mentioned is that the architecture focuses on linear operations. So how could we extend it to also have good performance on nonlinear operations? Does anyone have an idea here? Okay, then let me tell you what I found. As one idea, as before, could be to separate the processing units and have specialized stuff for the nonlinear operations, essentially just following the design principles of this functional slicing and have a special slice for everything. This could be used to effectively perform nonlinear transformations of input before passing it to the next layers in the stream. And we could even hardwire some common activation functions like ReLU or sigmoid. This could potentially benefit CNNs or RNNs. You can see here which activation functions are commonly used, and you can see that the evaluation range is quite small. So we could certainly do that. You can find related research here. First of all, we have activation function core for neural network implementations from Technological Institute of Sonora, or answer fast accelerating BERT on the Tensor streaming processor from 2022, which was actually published by Grok Inc. themselves, so they thought about this as well. And another approach could be to use something similar to transpim-lib. So what is transpim-lib? This is a software approach that implements these transcendental functions through a library, and transcendental functions are just functions that do not satisfy polynomial equations. So these nonlinear things. This is intended for PIM, and it utilizes CORDIC-based methods and lookup tables. CORDIC-based methods such as iterative methods that use only bit shifts, additions, and table lookups to approximate these transcendental functions. You can see here how transpim-lib supports these different functions with which method. And the interesting thing here that I would like to mention is that this transpim-lib library was actually researched by E.H. Zurich from the Safari Lab here. The paper is called A Library for Efficient Transcendental Functions on Processing in Memory Systems. If you're interested on that. Good. Now, I've talked a lot about these C2C and low latency interconnect, but I never really told you how it actually works. So how could this architecture be scalable? The answer here is obviously this low latency interconnect. As a reminder, it's located here. But what is interesting is how we can prevent network contention if you use this. So assume you use a lot of these chips in the same cluster and you want to use them for computation, they need to exchange information. So how can we prevent contention in the network? Does someone have a suggestion? Okay, so the problem would be that in this network, assuming we have these 4 chips, let's say B wants to send something to D and A also wants to send something to D. They might both choose to use this link. So B sends something to this through this link. The link is fully utilized. So A wants to send something too, but B gives it a signal that it's actually utilized by applying back pressure on the data. So A stops sending, and A has essentially 2 different options. Either it waits out until the link is free, or it reroutes its data to a different link like this that goes through C. This is happening because each of these different chips computes their ideal routing on their own. So they have no idea what the other chips do in this network. This is also why A does not know that the link between B and D is already utilized. And the solution to this is to use software scheduled networks. This means that the data movement decision making is left to the compiler. And this essentially works because the TSP is designed to be deterministic. Everything is controlled by the compiler anyway, so we can also control this data movement decision making by the compiler. With that solution, the whole thing looks like this. So the software knows about all these different chips and obviously knows all about the data movements in the network. So it exactly knows that B wants to send to D, and it knows that A wants to send to D. So it can essentially tell A to go directly to D, and it can tell B to D, and it can tell A that it should not try to go through B because this is already utilized and go the other way. So the software knows all about everything and can schedule things more efficiently. If you're interested in more on that, you can take a look at these slides from Grok Inc. Synchronous Scalability for Real-Time AI and HPC. They thoroughly discuss how this low latency interconnect of their tensor streaming processor works in detail. Okay. Then I have one last thing here. Something that I always find important, especially if we are working with a new architecture. Are there any potential security risks? So with the design that we've seen now, are there any things that stand out as being maybe a bit risky in terms of security? Did someone find something there? So what I thought about was that it's the compiler must do a good job, right? Because everything is essentially left to the compiler. All this scheduling and reordering is entirely in the compiler's hands. So the compiler must do a good job. I do not know how severe this could be for potential attacks if it does not do a good job. But I found various resources like this paper here from IEEE from 2021, reorder buffer contention for speculative interference attack for speculation invariant instructions. This talks about an attack that uses poorly scheduled instructions. I know that this is not the same processing unit, but the point I'm trying to make here is that these kinds of attacks exist. So it might also be some kind of attack possible for the TSP. And this is basically an open question, and because we can never be 100% sure whether an architecture is fully safe or not. Yeah.
It says in the chat that power consumption can be exploited, and when some lanes or vectors are deactivated to adapt to the current workload, this will lead to less power consumption, and this might be exploitable by side channel networks.
Yeah, that could be the case, yeah, because essentially here is the thing that we would have to keep in mind here is that also the power consumption and the control over how much power is used and how many of these layers are actually active is also in the hand of the compiler in the end. So basically, if you can control the compiler, you can control everything. Okay. So are there any more questions to the discussion? Yeah.
So what happens in performance if the network exceeds 350 elements? It's also other aspects.
So the paper essentially mentions that the peak performance is for vectors at most 320. But they also give you the possibility to extend this, either by using multiple chips or then by introducing some kind of batch. So then you could also add the batching there. But they did not test how well this works, or at least they did not mention it in the paper. But I think it would still work fairly good, maybe not as perfect as it does now with less than 320, but it should still be fairly efficient, yeah. Okay, so then here are the sources, and then I would be done. Thank you.
Thanks very much, Sven. Can you hear me in the room?
Yeah.
So thanks very much for your presentation. I think you did a very good job at introducing this block architecture and have very interesting discussion points. Yeah, I just wanted to mention that. So from my background as more working kind of on the bioinformatics side of computer architecture, I think it's very interesting to see this block architecture as a case study, perhaps, where machine learning isn't the only application necessarily where we can benefit from the static scheduling. So, for example, in bioinformatics, we accelerate a lot of GPUs also, but maybe it's really often not necessary to have all this dynamic scheduling for many bioinformatics applications. So perhaps we can all get inspired by Grok and think about new applications or refinements of this processing paradigm. Anyway, I guess that's just a bit of food for thought. Thank you very much. I think it was a great presentation, and I wish everyone a happy Easter from my side. Mohammed, can we end the session here?
Yes, thanks, Joel. So please don't forget to take the quiz and fill the evaluation forms so you can enjoy your Easter break. Thank you so much for today. Thanks for the presenters and their mentors. I guess we are not meeting next week. It will be a holiday. Let me quickly verify. Yeah, so see you the week after then. Thanks so much.